Every time you use an internet search engine, a machine translation system, a face recognition system on your camera, or a social media website, a deep learning model is probably being invoked. The book I'll talk about today, Deep Learning by John Kelleher, will explain what deep learning is, how it works, what it is capable of, and its current limitations. Throughout the 7 chapters, Kelleher positioned deep learning within the broader field of machine learning, walked us through how deep learning processes data from input to output, presented a history of advances in the field, and described the most important deep learning architectures and fundamental algorithms. I highly recommend this book as he explained everything with comprehensive examples and is very resourceful. I have very little knowledge before reading this book, but it's still fun to read. But if I misunderstood any part of the book, please let me know. So a lot of things he mentioned in the book are highly relevant to what we are learning in class. Particularly, understanding the logics of deep learning will guide us while making new art and designing new products. And issues raised, such as the transparency of deep learning algorithms and its impact on individuals, are something we need to keep in mind as designers. And before we go into the book, I want to talk a little bit about the author. John Kelleher is a researcher and academic leader of the Information, Communication, and Entertainment Research Institute at Technological University Dublin. He's the author of Deep Learning, co-author of Data Science, and the co-author of Fundamentals of Machine Learning for Predictive Data Analytics. And all three of them are on the MIT Press, and the first two are in their Essential Knowledge series. So, what is deep learning? We all know that deep learning is an artificial intelligence technology that enables computer vision, speech recognition in mobile phones, machine translation, driverless cars, and other applications. But indeed, it's a subfield of machine learning that focuses on deep neural network models. Therefore, it's important to understand first what machine learning is, and second, what neural network is. A machine learning algorithm is a search process designed to choose the best function from a set of possible functions to explain the relationships between features in a dataset. One example is the machine translation. Machine learning algorithms will take sentences in one language as input, choose the best functions that will make the input arrive at output, which would be the sentences in another language. After learning the function, I'll be able to apply it to new sentences and give the output as the translations. As shown here in the process, machine learning would prepare the data, which is a set of historical examples, and come up with a set of functions that the algorithm will search through to find the best match with the data. Then they do some measure of fitness that can be used to evaluate how well each candidate function matches with the data. And all three of these ingredients must be correct if a machine learning project is to succeed. However, when the information given in the problem is not sufficient to find a single best solution, machine learning algorithms may overcome it by supplementing the information provided by the data with a set of assumptions about the characteristics of the best function, and use these assumptions to select the best function. These assumptions are known as the inductive bias of the algorithm. If the inductive bias of a machine learning algorithm is too strong, then the algorithm will ignore important information in data, and then the returned function will not capture the nuances of the true patterns in the data, which is referred to the function underfitting the data. If the bias is too weak, the function is likely to fit the noise in the sample of the data and cannot give a good return on new input. During a machine learning project, a lot of time and effort is spent on identifying or redesigning features that are useful for the task the project is trying to solve. The advantage of deep learning is that it can learn useful derived features from data automatically. Let's see how neural networks enable that. So, what is a neural network? While explaining this, Kelleher links back to how brain works to help us understand the analogy between the structure of the human brain and the computational models. A neural network is a computational model that is inspired by the structure of the human brain. The brain is composed of a large number of interconnected and simple units called neurons. The functioning of the brain can be understood as processing information, encoding as high or low electrical signals, or activation potentials that spread across the network of neurons. And each neuron receives a set of stimuli from its neighbors and maps these inputs into either a high or low value output. All computational models of neural networks have these characteristics. And Kelleher uses this figure of artificial neural network to explain the structure. Think of the neurons in a neural network being organized into layers. The depicted network has 5 layers, 1 input layer, 3 hidden layers, and 1 output layer. A hidden layer here just means a layer that is neither the input nor the output layer. Deep learning networks are neural networks that have many hidden layers of neurons, and the minimum number of hidden layers necessary to be considered deep is 2. However, most deep learning networks have many more than 2 hidden layers. I find this very interesting that the depth of a network is measured in terms of the numbers of hidden layers plus the output layer. I will quote his explanation here as I find it very comprehensive. So in this diagram, the squares in the input layer represent locations in memory that are used to present inputs to the network, and these locations can be thought of as sensing neurons. There is no processing of information in these sensing neurons, and the output of each of these neurons is simply the value of data stored at the memory location. And the circles in the figure represent the information processing neurons in the network. Each of these neurons take a set of numeric value as input and maps them to a single output value. Each input to a processing neuron is either the output of a sensing neuron or the output of another processing neuron. So the arrows illustrated how information flows through the network from the output of one neuron to the input of another neuron. Each connection in a network connects 2 neurons, and each connection is directed, which means that the information carried along in this connection only flows in one direction. Each of the connections in the network has a weight associated with it. A connection weight is simply a number, but these weights are very important. The weight of a connection affects how a neuron processes the information it receives along the connection. And in fact, training an artificial neural network essentially involves searching for the best set of weights. So like traditional machine learning, a neuron also implements a 2-stage process to map inputs to an output. As seen here, the first stage of processing involves the calculation of a weighted sum of the inputs to the neuron. Then the results of the weighted sum calculation is passed through a second function that maps the results of the weighted sum score to the neuron's final output value. For example, here, an image recognition system would take a photograph as input and attempts to output and label. Both the input and the output are encoded in a way that neurons can compute. The photograph is represented by the list of red, green, and blue intensity values from 0 to 255 in every pixel, and the neural network mathematically converts this into a number, and the number of labels that have been defined in an image label dataset. The general process of improving the weights of the model is to select an example from the dataset and feed these input values from the example into the model. This allows us to calculate an estimate of the output value for the example, and once we have this estimated output, we can calculate the error of the model on the example by subtracting the estimated output from the correct output for the example listed in the dataset. Using the error of the model on the example, we can prove how well the model fits the data. The general process for updating the weights of a model in order to fit the model to a dataset is the learning process at the core of deep learning. And some chapters in this book gets into very detailed technical iterations of how, for example, linear and nonlinear mappings, as well as like training neural networks models. And I wouldn't go deeper into that, but it's worth reading. Lastly, I want to talk about CNN and RNN, the two deep neural architectures mentioned by Kelleher that are the most popular today. CNN stands for convolutional neural networks, and they are ideally suited to processing image and video data. Convolving a kernel across an image is equivalent to passing a local visual feature detector across the image and recording all the locations in the image where the visual features was present. And the main application include here classification, object detection, and semantic segmentation. And RNN stands for recurrent neural networks, are ideally suited to processing sequential data such as speech, text, or time series data. The depth of an RNN arises from the fact that the memory vector is propagated forward and evolved through each input in the sequence. And as a result, an RNN network is considered as deep as a sequence is long. The author also mentioned GANs, which we looked at in class, a generative adversarial network. The core idea of a GAN is based on the indirect training through the discriminator, which itself is also being updated dynamically. This basically means that the generator is not trained to minimize the distance to a specific image, but rather to fool the discriminator. And this enables the model to learn in an unsupervised manner. Imagine training the thief to avoid the police, and you end up having the best thief and the best police. So looking at the future trends, Kelleher talked about the development in biotech and other facilities that processes data on a daily basis. He also talks about the emergence of new models, new forms of hardware, and the challenge of interpretability. I want to talk about this a little bit, as the legal status of a right to explanation is currently vague, and the scale of the networks, the distributed nature of the representations, and the successive transformations of the input data as the information flows deeper into the network makes it incredibly difficult to interpret. So hence it's hard to explain how the network is using an input to make a decision to end users. It raises a lot of concerns about the tension of power between AI and human beings. I'll end here for today, and I have these questions for you to think about. One, what are some examples of machine learning following the wrong bias other than the ones we talked about in class, and how can we as designers avoid these existing bias? And two, can you think of any future applications of deep learning in solving any social issues in the US? And three, how can deep learning algorithms take advantage of the rapid growth in big data and computational power?